So we're in the midst of talking about reinforcement learning. Last time we introduced the basic reinforcement learning algorithms. And this is going to be the second lecture on reinforcement learning, where we generalize to larger state space models and we explore policy-based algorithms that will allow you to learn policy directly. So this is going to bring us closer to the state of the art of what people are actually doing in reinforcement learning. We started with MDPs, we understood what they are, we looked at Q-learning and SARSA and all these things, and now we're building up to, hopefully by the end of this lecture, you'll have the key ingredients to understand basically any sort of cutting-edge RL algorithm. Okay, so let's start by reviewing reinforcement learning. So remember, reinforcement learning is more of a setting than necessarily a particular algorithm. And the setting is very elegant. It's, in some sense, the most general way to, I think about AI. You have an agent. The agent takes actions in an environment, and the environment gives rewards and observations back to the agent. And along the way, the agent is meant to make sense of the reward and observations and choose better actions for subsequent iterations. So in what we'll study, the environment is defined by a Markov decision process. Remember the flaky tram MDP problem, where the goal is to go from location 1 to location 6 in this case, where the tram can fail with probability 0.1. Walking goes you from I to I plus 1. Tram goes from I to 2 times I. Okay. And the agent in this setting is going to be an RL algorithm. And we looked at multiple RL algorithms last lecture. In particular, we looked at Q-learning, where you define some sort of exploration policy, which might walk or tram randomly. And then we looked at epsilon greedy, where the exploration, the get action function would either choose to explore according to this policy or exploit the policy that it's learning along the way. And then the learning rate governs how quickly the RL algorithm is taking steps to estimate its Q values. Okay, so the RL algorithm, and here's what an example interaction looks like. This is from the agent's perspective. So remember last time there was a simulate function which called the environment and called the agent, but I'm sort of inlining this trace to see what the agent would be called with. So initially you start in state 1. So the environment says, give me the action at state 1. Okay. And then the action goes into the environment. And then the environment comes back says, okay, here's what happened. You were in state 1. You walked to state 2. You got a -1 reward and you haven't ended yet. Okay. So now the environment calls the agent with get action at state 2. And then the agent might go return, let's say it returns walk, and ignore this tram that's out of date. And the environment would say, okay, agent, here's what happened. You were in state 2, you walked, you got into state 3, reward -1, you still haven't ended, and then it will call the agent again and say, agent, in state 3, what would you do? And the agent might say, I'm going to take the tram now. And then the environment will update and say, okay, agent, in state 3, you took the tram, you end up in state 6, and you got a reward of -2, and now you're done. Okay, so this is a particular rollout, and each rollout generates a utility, which is a number which represents the discounted sum of rewards. So you take these rewards, and if the discount is 1, then the utility is -4. -1, -1, -2. Okay? Okay, so in particular, it's important to remember the isolation here. The RL algorithm doesn't see the MDP. We're not passing the MDP into the RL algorithm. It just sees everything it sees is through get action and incorporate feedback. In particular, incorporate feedback, that's the glimpse of the world it sees. And it's using that feedback to try to figure out what to do next. Okay, so if you generate a ton of rollouts, let's say 20 rollouts, and you average the utilities of all those rollouts, that defines the value of this RL algorithm against this MDP. Okay? So remember, a policy is a fixed mapping from states to actions. Our RL algorithm is a dynamic object that will update its internal policy as it learns from interacting with the environment. All right, so that's the RL setting. In order to define algorithms, RL algorithms, it's useful to define a bunch of different types of values. We saw all 4 values. Let me just put them here just so we have a reference here. And a value is synonymous with expected utility. So we first saw V pi of S. This is a number that represents the value of following policy pi from state S. If I got dropped into state S and I follow policy pi, and I did infinite number of rollouts, what would be the expected utility? That's what that number represents. Q pi SA is the value of in state S of first taking state action A and then following policy pi. Remember, these are the Qs are on those chance nodes, and Vs are on the state nodes. And now, if you replace the pi with stars, we're basically saying take the optimal policy and do that. Okay, so V star is the value of following the optimal policy from state S, and Q star is first taking an action A and then following the optimal policy. Okay, so now we define all these values. There's a question of how do you, what is your RL algorithm to model or not to model? So if you're model-based, that means you first estimate the MDP, and we saw how to do that last time. You just count the number of transitions and record the rewards that you see along the way. And then you compute the optimal policy using value iteration. And then what we saw was the first type of model-free method, which is a value-based approach, where we don't bother to estimate the transitions and rewards directly. We don't estimate the MDP. Instead, we estimate the Q values directly. And then once you have the Q values, if you have this Q value, you basically look at the action that gives you the highest Q, and that's your policy. So going from Q to policy is relatively straightforward. Going from reward or MDP to Q values is not as straightforward. Okay, so for the value-based methods, the general form of the algorithms, and this applies to model-free Monte Carlo, SARSA, and Q-learning, is we're estimating QSA. And when we get a piece of feedback, we have some sort of new point of view on what Q of SA should be. No one tells us QSSA directly, but we have some sort of noisy estimate. And we're going to call that a target. And a target is an estimate of the utility. And then when we do the update, we basically simply take our old QSA and we move it in the direction of the target by amount that depends on the learning rate. So if the target is already QSA, then this doesn't do anything. But if the target is above QSA, then we're going to nudge it towards target in that direction. Okay, so a few more things. So there's a question of on policy or off policy. Okay, so what does this mean? So in general, in our algorithm, you are following some policy, let's call that the exploration policy, to generate rollouts. This is a policy that is giving rise to the feedback. Now, using that feedback, the algorithm is going to estimate the Q values of a policy which we call the estimation policy. So in on policy, all it means is that the exploration policy and the estimation policy are the same. So the data that you get comes from the policy that you're trying to estimate. And off policy just means that the data that you generate is from a policy that's not the estimation policy. So when we looked at SARSA, that is an on-policy algorithm because SARSA tries to estimate Q pi, which is the Q values of the policy that you're following. And Q-learning was off-policy because you're trying to estimate Q star. So in Q-learning, the really interesting thing is that you could be following a random policy, but you're estimating the Q values corresponding to the optimal policy. So off-policy algorithms are very, very nice because then in some sense you can take data that comes from some source and then use it to estimate a policy that you want, which is often going to be the optimal policy. Okay, so what to use as targets. So remember the general form of the algorithm is that you're going to estimate Q and you're going to update towards the target. So there's two things we looked at. One is full rollouts, which just means that from state S, you actually roll out all the way to an end state, and then you take the discounted sum of rewards, and that's a utility, and that number is what you use. But the problem with that is that you have to wait until the end to get a number that you can estimate earlier on. And bootstrapping says, let's not wait until the end. I'm just going to get initial reward, and then instead of rolling out to the end, I'm just going to use my current estimate to estimate what kind of future utility I'm going to get. Okay, so I'm bootstrapping my utility from a model estimate. Okay, so in light of all these concepts, we can now think about the four algorithms that we looked at last time. We first looked at model-based value iteration, where we estimate the MDP first and then compute the optimal policy using value iteration. We then looked at model-free Monte Carlo. And this says, basically, you follow some policy pi. We're going to just look at the full rollouts from a particular state and taking a particular action and set target equal to that utility. So there's no bootstrapping. I'm just using the Monte Carlo estimate of the utility. SARSA says, I'm going to still try to estimate Q pi. So I'm on policy, but I'm going to use bootstrapping, where instead of using a utility, I'm going to take the initial reward and then a discounted, and I substitute here the Q value of the successor state. So I don't bother to roll out and figure out what happened at the end. I'm just going to use the Q value. And then Q-learning is almost the same thing, but with one small change. Now I'm estimating the value of the optimal policy. So this is an off-policy algorithm. It's still using bootstrapping, which is why it looks like SARSA. And the only difference is I stick a max over A here instead of letting A prime be pi of S prime. Okay. So I know that was a lot. Hopefully, what I'm trying to do is try to break it down into essentially the principal components: off-policy versus on-policy, model-based versus not model-based, bootstrapping versus not bootstrapping, and so on, so that you can see each of these algorithms not as an isolated thing, but see the kind of the rich interconnections between them. Yeah, so the question is, when would you choose SARSA, let's say, versus Q-learning? Okay, so the difference between them is on policy, versus off policy. So I think the short answer is it depends on your particular application. But the nice thing about off policy is that you can explore more aggressively and still be guaranteed that you're estimating the optimal policy. Whereas if you use SARSA, as you kind of run the algorithm, you essentially have to play much closer to the optimal policy, because otherwise you would be estimating the Q pi of the wrong, not the optimal pi. So the question is, what's the difference between SARSA and Q-learning, and what does this really mean? So remember, this target is what is computed when you do incorporate feedback, right? And incorporate feedback, you compute the target and then you update the Q values, okay? The get action is actually the same for SARSA and Q learning. If you do epsilon greedy, you either explore or you take the current Q value and choose the best action from there. So now if you look at this, in some sense, it's the same difference as if you remember when we looked at policy evaluation and value iteration. In policy evaluation, the recurrence is essentially taking the single action that is given by the policy. And in value iteration, you're taking a max over possible actions. And this reflects the objective here. So if you're interested in what is the target supposed to represent? The target represents, okay, I'm at a particular point, I get some reward, and then I'm going to, Q pi means I'm following the policy pi. So that's why A prime has to come from policy pi. Whereas Q star means I'm going to follow the optimal policy. And that's why there's a max over A prime. Because if this were the really true Q star, max over A prime would be the best action. And that would be the action taken by the optimal policy. So Q learning is trying to estimate the optimal Q values. Yeah. And the actions it takes, it depends on the exploration policy, but it need not be optimal. Okay, let me move on. So far, we're estimating a Q value for every state action pair. So this is called the tabular setting in reinforcement learning. And the reason it's called a tabular setting is essentially you have a lookup table, literally a dictionary, how we implemented it last time, for every state action pair. Okay? But now, in real world settings, you can't do this. For example, if you're trying to learn a robot policy, your state might be an image of what the robot sees, and your action is going to be how you're going to move the robot arm. Or if you're doing things with language models, your state might be an entire sentence or a paragraph, let's say, and then your action is to generate the next token. Okay, so in each of these cases, the state space is huge. It's all possible images or all possible sentences, so you certainly can't have a lookup table for that indexes by an image. It just makes no sense. So how should we deal with this? Any ideas? Yeah, so the suggestion is you have to reduce the state space. Yes, yeah, you definitely have to reduce the state space to maybe some smaller amount, and then you could do, Q learning or whatever on top of that. That's certainly one thing you could do. I think what we're going to do is to try to get even more directly at the problem. But I think the intuition of state space reduction is right. Okay, so function approximation in the context of reinforcement learning is used to contrast with tabular learning. So nowadays, with deep RL and all of these things, function approximation is already just a given because whenever you have a large state space, there's no other choice. So remember, the tabular setting is you have a lookup table. For every SA pair, you have a number QSA that you're storing. And function approximation says, wait a minute, what do we learn from machine learning? What we learn from machine learning is that you can actually learn very complicated functions of very high dimensional inputs. So S and A, let's say they're an image or a sentence, they're very large things. We know how to map that into a number, right? So why don't we just parameterize this function with some parameters theta and then try to estimate the parameters theta directly or estimate the parameters theta instead of trying to estimate Q directly. Okay, so this is the idea behind function approximation. So we'll see some examples. So now, recall the machine learning lecture. Okay, so what do we have to figure out? We have to figure out what are the possible functions. That's a hypothesis space or hypothesis class. How do we know whether a particular Q theta is good or not in the context of reinforcement learning now? And what algorithm do you use to reduce the loss? Okay, so this should all seem familiar. And essentially, we'll be able to incorporate many of the ideas from machine learning now into the RL context. So if you can extrapolate, take everything we learned from RL and everything we learned from machine learning, and we're just going to put them together now. Okay. So what possible functions can you choose here? S and A can be sentences, they could be images. So typically what we're going to do is we're going to map this into a vector of features, because machine learning likes taking vectors and matrices and tensors. And then we could use a linear function, simply a dot product between some parameter vector theta and a feature vector phi of SA. Or we can use a multi-layer perceptron, which we saw before. We simply take this vector, we multiply by a matrix, and then we apply some nonlinearity, and then we multiply by another vector or a matrix and keep on going. I'm not going to talk too much about what are the choices here, but just think about this as a place where you drop in your favorite model architecture. Okay, so let's try to work an example of this. So define the same environment as before with this MDP. And now we're going to define the same exploration policy. And now we're going to do parameterized Q learning. And for this, so what I'm going to do is, just for simplicity, we're going to assume that the state action pair just maps into indicator features. So we have one feature for every state action pair. So this will allow us to use machine learning to simulate the tabular setting, so we can just check that everything is working. But just then, hopefully you can use your imagination to drop in other more powerful machine learning models. Okay, so here in the class, I'm going to have my linear model here, which maps from number of features to a single scalar representing the Q value. And I'm going to have my optimizer handy. Okay, it's just going to be SGD. Okay, so let's figure out what this feature vector should look like. So conceptually, I'm just going to map the state action pair into essentially a number between 0 and the number of states times number of actions minus 1. Okay, so that's all this is doing. States are number 1 through 6, so I'm going to make it through 0 through 5, times number of actions plus the integer representation of that action. So in that case, this is 0. I create a one-hot vector of length, number of features. So this is going to be the feature representation of one walk. This is going to be the feature representation of one tram, 2 walk, 2 tram, and so on until I get to 6 tram. Okay, so every state action pair is just a different feature vector. Okay, so this is all hand-coded, no learning here. All right, so now I have, I'm going to compute Q values of a state and action pair. And to do that, I'm first going to map this into feature vector space. And then I'm just going to pass it through the model and I get some number out. Okay, so that's going to be how I compute the Q value of a particular state action pair. Okay, so now given that I know how to compute Q values, I can compute policies. And the policy that I get at state 1 is going to be compute Q values for all the actions, and then choose the action that has the highest Q value, and that's going to give me my action that I return for my policy. Okay, I'm showing you essentially how to compute the feature vector, the Q, and the pi, given a fixed set of parameters now. Okay, so now we have the building blocks. Now we can implement get action and incorporate feedback, which is what every RL algorithm needs to do. Okay, so what happens now in get action? This is the same as actually before, where I run epsilon greedy with probability epsilon, I explore. And with 1 minus probability epsilon, I don't explore. And now let's incorporate the feedback. Environment says, I walk to state 2. What should I do with it? Okay, so now I'm going to compute the target. So in order to compute the target, I'm going to look at self-dot pi of next state. Remember, pi is going to take the argmax over the Q values, and that's going to give me the optimal action given my current Q estimates. And then I'm going to compute the target to be the immediate reward plus the discounted, and I'm using bootstrapping, so I'm just plugging in the Q value of the next state and the next action. Okay? So now I have the target. I also have the predicted value of if I'm in state and action and take action, what is the value that I expect? And I want this to be close to target, right? And remembering regression, what do we do when we want two things to be next to each other? We define the loss to just be the standard squared loss, which penalizes deviations between the prediction value and the target. So now that I've defined the loss, I can just compute the gradients with respect to that loss. This is just standard PyTorch, and I update the parameters. Okay, so hopefully you can see now how the machine learning enters the reinforcement learning. Basically, all the skeleton of get action, incorporate feedback, and how to Q-learning is basically specifying the target. Now, given the target, now all this loss calculation and model architecture, that's just within the realm of machine learning. So now I did this for Q-learning. You could imagine doing this for SARSA or model-based model-free Monte Carlo as well. And it sort of plugs in. Okay, so now maybe you go back and you say get action. And now 1 minus epsilon probability, I'm just going to choose the optimal action that I have so far. And then I incorporate feedback, compute the target, compute the predicted reward, form the loss, compute the gradient, update the parameters. And then get an action. This time I'm also exploiting, and then incorporate feedback. I get, I'm at the end, so there's no next state, no next action, so that's just the reward. But nonetheless, that's still a target that I can update against, compute the loss, compute the gradient of the loss, and update the parameters. Okay, and if you simulate this 100 times, then you get some weights and you get some value. Let's look at the optimal policy that has been computed. So what I'm doing here is for every state, I'm going to call the RL algorithm's pi function to get me what is a policy that has in store for me. And I guess this time it didn't. Okay, maybe I got unlucky here. So this is stochastic, so it didn't actually end up with the right policy here because it should have walked, and then took the tram, but it didn't do that. But if I ran it for longer, it should do something reasonable. Okay, so what I'm doing here with this policy is I'm also looking at the estimate of the optimal values, which is taking Q state and pi state, and I get these values. Let's compare it with the true values by solving the MVP. So remember I had the original MVP, I just call value iteration on it. And the original MVP is not available to our algorithm. So I can't do this actually in our algorithm, so I'm doing it outside. And I get the result. And the result, if you look at the actual values, these are the true optimal values of the MDP. This is what the RL algorithm came up with. It's sort of kind of doing something reasonable, but it's sort of off. And this is the actual optimal policy. Okay. Well, I think I got unlucky here because in the previous iteration, it did get the optimal policy. So to summarize, what we're talking about is function approximation. You have large state or action spaces, and you can't use the tabular setting. You can't just look up this, all possible images or sentences. So what we're going to do is parameterize the Q value by some either linear or nonlinear mapping from state actions to some value, number. We're first going to map a state action pair into a vector of features. And then we're going to define either a linear function or MLP to map the feature vector into a single number. When we do incorporate feedback, we're going to define the squared loss between the predicted Q value and a target, which is given to us by the virtue of doing Q learning. And then we're going to take a gradient of this loss function with respect to theta and take a step in that direction. So the question is, why is the loss function the square difference between the prediction and the target? So the intuition here is that the target, so let's see. Maybe the easy way to explain this is that suppose your target in model-free Monte Carlo is just a utility that you get from a full rollout. Okay? So if you did that 1,000,000 times and took the average, that average would be the value you would want. And now, so target in some sense is representing a noisy version, in general, a noisy version of what you want. So when you form the squared loss, it's saying like you're doing regression. You're saying, I want the value to be close to target. So now when you update the parameters of the model, after you update the parameters, the loss goes down. And the only way the loss can go down is value moves closer to target. So the question is, does this method converge to the optimal value? In general, no. In the tabular setting, there are some conditions in which Q-learning will converge. Usually these things look like your exploration policy needs to just be everywhere. And if that's the case, then I think generally it will be fine. But now if you put in function approximation, in general, there's no guarantees. You might be able to show convergence to a local optimum, but that's maybe less exciting than showing that it's finding the optimal policy. So now we're going to move on to a different way of doing RL. Okay? And this is the space of policy gradient or policy-based methods. So if you remember where we started with model-based RL, which means we'll estimate the MDP first, and then use that MDP via value iteration to compute the optimal policy. And then we said, wait a minute, we don't need the MVP. Why don't we just compute the Q values directly, and then using the Q values, we can just get the policy by taking the action that gives us the largest Q value given a state. These are called value-based methods. But now if you're paying attention, you said, wait a minute. Actually, we don't even need the Q values. We can just directly estimate the policy. Why don't we just do that? Okay, am I just wasting your time here? The short answer is no, but the long answer hopefully will become clear later. So the way to think about a policy is just a classifier, right? What is a classifier? It maps inputs to outputs. So everything's a classifier in some sense. So the input here is a state, and the output is an action. Okay? So if you remember the machine learning linear classification lecture, we said that, well, these classifiers are actually really hard to optimize because you end up with like 0-1 loss and the gradient is 0 everywhere. You can't do that. So what do? We made probabilistic classifiers. So we have a probabilistic classifier that takes an S, a state S, and then defines a distribution over possible actions. And distributions are continuous, and therefore we can optimize them. Okay. So that's the prelude. Now let's talk about imitation learning for a little bit. So if we had demonstrations of that policy, this would be actually, we could just go home. And what is a demonstration? It's basically having an expert that gives you a rollout of, so a expert came along and said, okay, here's what you do. You walk to state 2, you walk to state 3, you take the tram to 6, okay? And then if you have that data, you could say, okay, well, I'm going to turn that into a bunch of examples for my training algorithm. I said, if the input is 1, I want to walk. If the input is 2, I want to walk. If the input is 3, I take the tram. 3 examples. And then you could say, I'm going to define an objective function, j of theta, which sums over all the examples and looks at the log probability of an action given the corresponding state. Okay, so this is called imitation learning because you're having an expert that shows you what to do, and now you just train the classifier to /policy to just do whatever the expert said. Okay, so for example, this is actually done in context of what would otherwise be RL problems. So in robotics, you have people that tell or operate a robot that says, okay, here's how you pick up the cup and put it on the counter without breaking it. And in math, companies will hire people who know math to go and solve a bunch of math problems and write nice solutions. And those are demonstrations of what an expert would do in a given state. Okay, so you don't need our algorithms for imitation learning. It's just supervised learning. Okay, well, that was easy. But the problem is, what happens if you don't have demonstrations? Remember the RL framework? The environment's not nice enough to give you, here's what you should do. The environment is cruel. It'll just give you reward or no reward. So all we have this reward function. So what should we do? Yeah, you can explore. Great. So all you can do essentially is roll out your policy, get some data, but you don't want to just roll out and then just clone that data. You don't want to do whatever that data tells you. But along with that data, it told you essentially how good that outcome was. And so a crude thing you might think about is, well, I'm going to roll out, and some of the trajectories are going to be good, and some of them are going to be bad, and I'm just going to take the good ones and then do imitation learning. And you wouldn't be too far off from what actually happens. So if you just want to remember like kind of the 0th order thing, in policy gradient, you basically just roll out your policy, you collect a bunch of rollouts, and you take the ones that have high reward and you do imitation learning on them. Okay? In the rest of the lecture, I'm going to give you something a bit more nuanced than that with more math, but the intuition hopefully is clear. All right, so let's get going here. So we have this rollout. Okay, there's going to be more math in this section than in previous sections, just so you're aware. Put on your math thinking caps. Okay, so we have this rollout. I'm going to use tau to denote. Tau stands for trajectory. I'm using the term rollout. I think rollout trajectory episode you can maybe think interchangeably. So a rollout says it's basically state, action, reward, state, action, reward, state, action, reward, state. Okay, so a concrete rollout looks like the thing that we've been looking at before, where you have walk, tram. And remember, each rollout produces a utility. Okay, so that's standard. Now, what is a probability of a rollout? Okay, what I mean by this is what is the probability that this thing happened? And by the chain rule, we can write this down as a set of conditional probabilities. It's the probability of starting S0. In all our settings, it's been deterministic, so this is just 1 for, if assuming the first element of tau is S0. And then the first thing is that there is a policy pi theta. What is the probability of taking the first action given S0? And then times the transition probability of from S0 and A1 transitioning into state S1. And now it's the agent's turn, probability of A2 given S1, and environment's turn, probability of S2 given S1 and A2. And then there's the agent's turn and the environment's turn and so on. Okay, so the probability of a trajectory is this interleaved sequence of probabilities of the agent, policy, the environment transition, agent transition. Okay? So the components are, just to say it again, there's a policy term, and then there's the transition distribution term. Okay. Okay, so now if you just think about what we're trying to do in reinforcement learning. All we're doing is trying to find a policy that maximizes the expected utility of a rollout, right? So I can just write that down directly. So V stands for value of theta, and theta, remember, are the parameters of the policy, is equal to the expectation of the utility of tau. Okay, expected utility. And if I write that down, it's basically thinking, well, what is the expectation over? It's expectation over all possible trajectories tau, and the probability of that trajectory times the utility of that trajectory. Okay? So there could not possibly be a more direct statement of what RL should be doing, right? You're literally saying expected utility, and we just want to optimize this. So no MDPs, no Q values. This is in some sense the most direct thing you can do. Now, how do you optimize this? We've only learned one way to optimize a function. Gradient descent. Okay, so let's just take the gradient. Okay. Yeah, there's this expectation here that might be a little bit annoying, but let's do it anyway. Okay, so let's take the gradient of V theta with respect to theta. Okay, so gradient V, I'm just writing down the definition of V. So far, so good. I'm going to expand the definition of expectation to be this explicit sum over p theta of, let me just make this larger, help the audience in the back. So this is the expectation over all trajectories. So this is summing over all trajectories, probability of that trajectory times utility of that trajectory. Okay, so these are just definitions. I'm going to move the gradient inside the expectation or the sum because gradients are a linear operation. Okay, so now I'm going to do something. Okay, so what is the gradient of p theta? Okay, and you're probably like, well, I mean, it depends on what p theta is. It's just like it's the gradient of p theta. But what I'm going to do is something that might look a little bit strange at first. I'm going to rewrite it as p theta times the gradient of log p theta. Okay? So, okay, just so you're wondering, okay, where did that come from? It comes from, let's see. Let's do it this way. Okay, so what is the gradient of log of, okay, let me just write it down. Okay. So what's the gradient with respect to this? So remember, the gradient of a log is 1 over that quantity times the gradient of whatever's inside. Right? And then all I do is move this over here, and that's how I write this in terms of p theta times this. Okay, and there's a reason to this madness. Why am I doing it like this? It's because now I have something that's sum over trajectories times p theta of that trajectory. And I can neatly wrap that back into an expectation. So whenever you see this expectation, you should think about it as summation over trajectory times probability of that trajectory. Okay. So now I have the gradient of this thing above, which wasn't maybe obvious how to differentiate. Now I've written it into this expectation where I have the gradient of this quantity. And this identity is called the policy gradient theorem, but I mean, it's sort of elementary, so I just call it the identity. It's not really it doesn't deserve to be called a theorem. Okay. So this is actually good because in general, whenever you see an expectation and you want to compute it and you can't because it requires summing over like all possible trajectories, you can think, maybe I can just take a random sample from that. Okay? So that's what we're going to do here. We're going to replace this expectation with just a sample. So instead of summing over all possible trajectories and weighting by the probability of that trajectory, I'm just going to sample a trajectory, and then I'm going to define an objective function, j now, which is just this thing on the inside, log p theta tau times utility tau. And then can just take update theta by taking a step in the direction of this gradient. Okay, let me just pause here. I'll just kind of summarize. We started with this undisputable goal of maximizing expected utility. I said, okay, we only know how to optimize things by taking the gradient right now. So let's just take the gradient. The gradient is actually an expectation of stuff. And I said, you can just take a sample to approximate the full expectation. And now we're going to define this objective function whose gradient is exactly the thing kind of inside. So maybe just to foreshadow some stuff, what this is basically saying is that go ahead, explore, do your rollouts. Once you get a rollout, I'm looking at basically this term and weighting it by the utility of that, and then just updating it. So if I didn't have this utility, I would just be doing imitation learning, right? Just maximize the probability of the trajectories I saw. But now with the utility, it's sensitive to essentially how good this trajectory is. Okay, so I think something got a bit messed up in the formatting here. But if you think about unpacking this gradient term, this is going to be utility times a summation over all time steps of the probability of an action given the preceding state of overall time steps. And this is known as the reinforced algorithm, which comes from Williams 92. Is an instance of this general class of policy gradient algorithms, but reinforces perhaps the earliest and simplest one. And like I said before, the intuition here is that we're essentially performing imitation learning on demonstrations, which we know and understand. Demonstrations come from our own policy, but they're weighted by the utility. And if the utility were just 0 or 1, basically success or failure, then this is just imitation learning on the successful demonstrations. So the intuition that I mentioned earlier, which is do a bunch of rollouts of your policy and then just take the ones that are good and do imitation learning, is exactly what reinforced would do in this special case where all the utilities are 0 and 1. Okay? Now, if they're not 0 and 1, then you have a little bit more. If it's like utility is 0.5, then it's saying, well, I'm sort of have a weight of 0.5 on that example, a trajectory. And if the utility is minus 10, then I'm like running away from, I'm saying like, don't do that, don't do that. So yeah, what is this utility? Where is it defined? So the utility of a rollout, if you remember, is the sum of the discounted rewards. So when you have a rollout, it's just -1 times discount times -1 plus discount squared times -2. Okay, so hopefully this should be pretty intuitive, policy gradient. Just to summarize, optimize policy directly to maximize expected utility. Due to the policy gradient theorem or identity, we can compute an unbiased estimate of the gradient by sampling a single trajectory and then just updating that. And the algorithm is, you sample a rollout, which means that you're on policy, and then updating each state action pair in the rollout weighted by the utility. Okay, so now that we've gone through the math, let me try to implement it now. Okay, so we start with the same MDP, and now I have reinforce. Note that we don't need so reinforce, now I have a model that is going to essentially classify map from states to actions. So it's a probabilistic classifier over number of actions, so that's why it's a matrix now, because I'm multi-class. And then I have the optimizer as before. Now, like in model-free Monte Carlo, we're going to keep track of the current rollout as we incorporate feedback, because in the current algorithm, as I defined, you have to wait until you get the utility. Okay? So notice that we don't need an explicit exploration policy because we're defining these probabilistic policies now. And that should give us some exploration. Now, you could also add additional exploration as you want, but we don't absolutely need to here. Okay, so let's peek at what get action and incorporate feedback do. So get action, I'm going to compute a feature representation of the state, okay, which is going to be a one-hot vector representing the state here. I'm going to pass this feature vector through my linear matrix, and that's going to give me some logits. And then I'm going to take the softmax. That's going to be giving me a probability distribution over these actions. And then I'm going to sample according to those probabilities. And then I'm going to get the action and return it. Okay, so all get action is doing is what you would do in classification, where you compute the logits, get the distribution, and now I'm sampling from that distribution. So now what does incorporate feedback do? Like in model-free Monte Carlo, we're just going to remember the rollout for, in general. So remember the start state, keep track of the utility, add to the rollout. If I'm not at the end, I don't do any updates. I'm going to get action, incorporate feedback, get action, and now the last time when I incorporate feedback, I'm at the end. So here's my rollout, and now I want to update the parameters. Okay, so I'm going to keep track of the loss. I'm going to go through each step of the rollout. Each step of the rollout goes from some state to a particular action. So the first time it will be state 1 to taking walk. So remember, this is the input and this is the output of the classifier. So I'm going to now compute the model's prediction of the action given the state. So compute the feature vector, compute the logits. And now remember, in multi-class classification, I compute the cross entropy between the logits and the target, which is just a one-hot encoding of the action, in this case, walk. And then I add that loss. Okay? So I want these logits to match the target here. The format of the algorithm is the same. So you go through the second step, you add your cross entropy term for the second step, and then you go through the third step, and then you add the cross entropy term for the third step. Okay? I should be multiplying the loss by the utility. So now you update your parameters, compute the gradients of this loss, and then take a step. And now these are the updated parameters. Okay, so let's see what happens if I run it. And so I get here are the weights, get some value. I think it seems to have worked even though I messed up the algorithm. Interesting. Okay, so it learned a distribution where in state 1 I should walk, state 2 I should walk, state 3 I should take the tram, state 4 walk, state 5 walk, state 6 walk. Or I guess state 6 is the end state, so these values are just kind of arbitrary. Okay, so in summary, get action just samples from the policy, and incorporate feedback updates the parameters state action in the rollout, and waiting by utility, which I didn't do, but you should do. Yeah, this is online. All RL algorithms are generally online, unless it's offline RL algorithm, because whenever you're doing this, it's online. You're getting an action, you incorporate the feedback, you get action, you incorporate feedback, and so on. And here, this is just one rollout, and I'm already updating the parameters. Sometimes you might want to batch, like have a bunch of rollouts and you batch them up. So it looks a little bit more offline, but the spirit is online. So the question is, does the initialization of theta matter? In general, it does. Even in the standard supervised learning case, if you're training a neural network that is nonlinear, then initialization will affect the outcome. I think in reinforcement learning it matters even more because as currently implemented, the initial exploration policy is given by pi theta. So the data you collect will also be governed by the goodness of your initial policy. And in general, you want thetas to be set probably small so that you get a kind of a uniform distribution over your actions. Okay. So let me talk through a bunch of bells and whistles here. So recall the objective, maximize expected utility. So we can just write it down, and the policy ingredients theorem says, here is the gradient, and we can't compute the gradient exactly because that would involve summing over all possible trajectories. But what we've done is use reinforce to say, I'm going to get an estimate of that gradient by just taking one sample and computing the gradient of this one sample. Okay, but can you get better estimates? So to talk about what better means, I'm going to go through this quick detour of talking about variance reduction. Okay, so let's consider a simple setting where you're just trying to estimate the mean over a set of numbers. Okay, so I is the index into a list. Every number has a particular probability. So there's 4 numbers. Okay, this should be 0.25, 0.25. Probabilities do sum to 1. And the points are -4, -6, 6, and 8. And so you want the true mean to be basically the dot product between these vectors. And we'll just pretend these sum to 1 for now. I'll fix that later. Okay, so an estimator, to be formal, is any random variable that tries to get close to mu. So remember, mu is this thing that let's say it's expensive to calculate. Here, it's easy to calculate because you sum over 4 things. In general, you're taking the mean over all possible trajectories, which is hard. So each estimator has some sort of bias and variance and maybe some also computation cost and computing it. So the simple estimate of mu is you just sample a single index and you return the point at that position. Okay? So you might sample an index, and then you get the point, and then you return it. So every time you compute the estimator, you might get a different value. And then how do we know if the estimator is good? We have to compute its bias and variance. So let's just try 1,000 times. We're going to call the estimator function, and then we look at its mean and variance. Okay? So here, for this particular estimator, the mean is 1, which is what it should be. So I guess everything normalizes. So just imagine this is 0.25, 0.25. And then the variance is 36, which is not great if you think about it. So normally if you're doing stochastic gradient descent, high variance means that it's just going to take more iterations to get to the right answer. Okay, so here's another estimator. Why don't we just sample 2 2 points and then just average them. Okay, so if you look at that estimator, the mean is roughly the same, but the variance is a lot smaller. So in some sense, this is a better estimate of the mean. You can also make it worse if you, let's say you choose a point and then you just add some random noise to it. So if you do that, then the mean will still be roughly right. It's unbiased, but the variance is going to be worse, even worse than the original one. Okay, so now, here's comes the fun part. So now, suppose I have this magic function, offset, I. Okay, and this is going to have mean 0, which means that if I subtract this offset, this is the same as this by linearity of expectation. And then this part is 0, so that is the same, it has the same mean. Okay, so let's suppose I just define this offset to be -6, -666. Okay, so I'm going to sample a particular index, and instead of taking just that point, I'm just going to remove an offset. Okay, and I'm going to return it. So if I do this one, you'll notice that the mean is good and the variance suddenly goes down a lot. Okay, so this is magic, right? So I managed to reduce the variance by a huge amount without affecting the mean, right? It's easy to make the variance go down if you don't care about the mean. You just return 0, and then that's going to give you not a correct answer. But here, as long as I pick some function where the mean is 0, I can add it to my estimator and hope that I can reduce the variance. So this is, in statistics called control variance, is a general idea that's quite powerful. Okay, so let's see how, so going back to a reinforcement learning setting, how do we find an offset that has 0 mean and hopefully can reduce the variance? Okay, and just to provide some intuition, why is this working? This is working because if you think about it, the mean is 1, right? So the ones over here are sort of too far down, and the ones that are over here are too far up. So what this is doing is it's sort of pulling up the ones that are sort of like too far down and pulling down the ones that are too far up. So if I have some prior knowledge about where the mean might be relative to my points, then I can hope to reduce the variance. Okay. So here's the key identity. Okay, so I'm going to claim that I'm going to define a function b of s. It can be any function that only depends on the state, but not the action. Okay, then I'm going to claim that this quantity holds. So what is this? This is, remember, this is the expectation of the gradient of the log policy times this baseline. Okay, and this holds for all s and a that's drawn from this policy. I haven't proven this, but I'm just want you to stare at this for a moment. And if you think about why this is helpful, if you look here, the policy gradient theorem is this thing, right? So that means if this is 0, I can just add this or subtract this from that. And I don't affect the mean, but I have the chance of reducing the variance. So if you remember A star, there was this idea that the heuristics in A star are using domain knowledge to improve the algorithm, and if I can estimate the future cost, I can really get a very fast algorithm. So this is kind of an analogy here, where if I can figure out the right baseline, this B is going to be called the baseline function, I can actually vastly reduce the variance as well. Okay, so the proof is fairly straightforward. It goes like this. Okay, so let's just take the expectation of B of S. That is some constant. Okay, that doesn't depend on, in particular, it doesn't depend on theta. And now I'm going to take the gradient with respect to theta of this quantity, and the gradient is 0. And now, actually, in the interest of time, I'm just going to skip this and just trust me that this works out. Basically, it's the same math as I used for the policy gradient theorem, but just going in the other direction. And so using this idea, there are a few things. I just want to highlight them. I'm not going to have time to go into them in detail. The first is that using baselines. So I can just subtract a baseline from the utility, and as long as that function doesn't depend on the action, then I'm free to do whatever I want. And I can come up with, it can be a model, it can be some sort of heuristic, and that can reduce the variance. Another thing I can do is, instead of using the utility, at each step, I can use only the rewards from that point on. And this is valid because the past doesn't depend, it doesn't affect the future. And then finally, I can also plug in a biased estimate of the value function. So I'm going to bring back Q's. I'm going to say, I am doing policy gradient, but instead of using the actual utility, which is what I did in model free Monte Carlo, I'm going to bring back the Q's, which is what I did in these bootstrapping methods. Okay? And these methods are called actor-critic methods because they allow you to estimate a value and also estimate the policy at the same time. And in deep learning, you can even tie the parameters together. Okay, to summarize, the game here is to find an estimate of the gradient of the expected utility that has low bias and low variance. So by using baselines, this is a pretty general purpose strategy to reduce the variance, but it's still unbiased, which is good. Bias is 0. And you can also use bootstrapping to reduce the variance at the cost of some bias. And then finally, let me summarize this whole lecture on MDPs and RL. So we looked at 3 classes of methods for doing reinforcement learning. Model-based, estimate the MDP, compute the optimal policy. Value-based, directly estimate the Q values and derive the optimal policy. Policy-based, just directly estimate the policy. The form of the algorithm is similar in all 3 cases. You roll out with some exploration policy. You form some sort of loss function. It could be in terms of the parameters of MDP, Q values, or the policy. And you update the parameters using a gradient step. Okay, so that concludes MDPs and RL, where we're trying to maximize the expected utility. So what we're going to look at is what happens if there are adversaries in the environment and you can't really use expectation anymore. You have to consider what happens in the worst case.